The other laptop that I normally write with maybe is misbehaving. Who knows? And so I may write with this, and also this one I've also installed OneNote because somehow this Apple people want me to reset my Apple ID, and I forgot it, and now they gave me so many days so that it can be recovered. But I hope what I'm going to use may help us today. Maybe a tab. Let me try to. If this will work, well and good. If it does not, then we seek other means. Let me first try. So today we want to look at what we call the interpolation. So do you see something?
Yes.
Let's see if this other guy can wake up. Let us let him to rest. So basically, so at least we have seen how to solve systems of linear equations, and then we understand the basics. By the way, the reason why people focus on solving linear equations and nonlinear, I think maybe I don't know if you covered solving a linear equation somewhere, but most of the things we do will narrow down into solving systems of linear equations. Even if you look at the differential equations, if you look at the differential, be it partial or ordinary differential equations, their solutions numerically can come down into solving linear equations. That's why we focus on that part, and that's why that part is important. Those linear algebra. So you need to understand on why, when the solutions exist, when they don't exist. And so in some cases now, we are dealing with functions f of x, y is equal to f of x, where x can be anything. For now, we look at function of one variable. These functions can represent something which is very complicated, and so hence not easier to deal with. What we do basically is we try to find the values of the function at given data points or at given specified points. And so having that function defined at given points, we can now want to approximate the value of that function at certain values or at certain point, which might be intermediary points from where it's not given. So that process of trying to define a complicated function using a simple function, or trying to define a function which is only defined at specific values, is called interpolation. So that's basically what this interpolation is. So just to interpolate, we are just trying to, like, you are filling the holes. You have a function only defined as some values, but you want to describe that function on the entire interval. And so if you can define that function on the entire interval, then we are calling it interpolation, so that now you can approximate the value of that function anywhere else, not necessarily where it's defined. I'm just still seeing if these are so that I wanted them to have the notes to be one at one place where I can easily get one PDF. But if I have them now stored at different places, it will mean I get different PDFs. But so if it does not work, then we cannot force it. So we can at least maybe briefly at least just write something. So we are saying that mostly in this one should be serious. So I picked this, and then I need to pick this. So we are saying that in in most practical applications, uh, we find that most practical applications, we usually deal with a function f of x, or you can just say y is equal to f of x, which may not be explicitly defined. Or it's difficult, or it is difficult to handle. You may go to the field. When you go to the field, you do experiments, and when you do experiment, you measure the values against some other values, either at different data points. You are measuring some, so you have an input, which is data points, which can be time, can be something, maybe at different points in space, and then you measure the corresponding values of the output at the same data point. And so when you measure these values, you later want to approximate the output at certain values where you could not measure. So that's when we need the interpolation. Or you want now to define a smooth function that now can describe whatever you are measuring. So you're able to experiment, not to define. Or just some cases you find that you are dealing with a complicated function that you can't even look at to handle. So, but you want to represent that with a smoother and a simpler function that you can easily deal with. And in most cases, we deal with the polynomials because they are very easy to handle and very easy to deal with. And so if you approximate a function with a polynomial, we call it polynomial interpolation. And so to handle all is difficult. Or in some cases, so you say, or in some cases, so you're saying, or in some cases, we may have the function just defined at some tabulated points. And so in such some tabulated points, maybe say we can say what xi and yi. So xi is the input and yi is the output, where yi is the same as a function of xi, and xi is less than xi and then plus 1 for I is equal to 0, 1, 2, 3. So in short, what I'm saying is when you have those values, we arrange them, the tabular points or the data points, we arrange them in ascending order. And then we find now the corresponding output or the function, the corresponding value of the function at those data points. So basically, what we have is something like this. So we are having, I can have this I can have xi and then the corresponding yi. So here, these are just the node numbers 3, 4, 5, and then here we'll have x0, x1, x2, x3, and x4. Then we have y0 or y0, y1, y2, y3, and y4. So this is the case of what we have. So interpolation is just now trying to find the values inside. We can approximate the values where at these missing holes. So that's why we try to approximate the values. So if you have a function which is complicated, or you have a function which is defined only at some points, then we replace it with a simpler function. So that's what I'm saying, that if the above situation happens, then we replace the function with a simpler function. That coincides with, so the function you approximate with should be the same as the function we want to approximate at the tabular points. That coincides with f of x at the given n plus 1 or tabular n plus 1 tabular points. So these are just values that just because since we start from 0, so it will be n plus 1. So if this is n, so the points are 5. If n is equal to 4, then you have 5 data points. So we can say that this process is known as interpolation. Which one have I been using? I think this one looks better. Yeah. So the whole of that process is called interpolation. And if we replace f of x by a polynomial, then we call it what? We call it polynomial interpolation. So there are several ways of approximating functions. And first, those methods depend on the data points. If the data points are equally spaced, you're having points at equally spaced values, then we will see two methods, or methods mostly based on the newtons. So you have the newtons forward or newton backward interpolation. Otherwise, if we have points defined at the points, the data points are not equally spaced, then we have what is called the Lagrange interpolation, or interpolating polynomials. So we will consider the two cases of interpolation. And so we can now say that maybe, so in the first case, we consider polynomial functions where the tabular points. So tabular points are x0, x1, x2 until xn are equally spaced. So if they are equally spaced, that means the difference between the successive values is the same. And so we can find h, or so what am I saying? That is, if they're equally spaced, it means xk plus 1 minus xk is the same as h for k is equal to 0, 1, 2, 3, and so on until n. So this number h is called the step length, or the thickness, or the height, whichever you want to call it. So the real number h is called the step length, or the height, or the thickness. And so since these values are equally spaced, it means if we know the height and we know the first one, we can generate all the other data points by saying that xk is the same as what? You just x0 plus kh. And so in this case, we assume I will use this notation. So when I write yk, I'll mean the value of f evaluated at the nodal point k, xk, or x subscript k. And so here it means if k is equal to 0, we get x0. If k is equal to 1, we get x1. If k is equal to 2, we get x2. So basically, so what are we saying at this point? I'm just saying, for example, x1 is equal to x0 plus h. And remember, x2 is equal to x1 plus h. But what is x1? X1 is x0 plus h. So this is x0 plus h plus h, which is the same as what? X0 plus 2h. So just what we are saying here. So this was just to illustrate. If you want, you can keep it somewhere. Any question? But you know, today I cannot even see you. Let me first join with my phone also to the meeting. You know, if I don't see in the background, naweza kuwa naongea na jamaa ameenda kulala bwana. Can you? Unajua kama naweza kuwa naongea na jamaa naona huko. Naweza kuwa naongea na kumbe jamaa ameenda kulala. Unajua ni kama anasemanga tu but this different beyond logo. Let me see. I don't want the term. The link. No, I don't want the Microsoft Teams one. So join with this account.
You are muted because a lot of people are on this call.
Oops. This is stupid one is. So, can you hear me?
Yes, we can hear you.
Okay, so at least now I can see if people are sleeping. So until this point, do you have questions? So if we want to deal with interpolation of functions where the functions are, no, the data points are equally spaced, then we deal with things which are called the difference operators. So they are so first I'm going to introduce here what we call the difference operators. They are the quantities we will need for us to approximate a function given data points which are equally spaced. And the first one I'm defining is called the forward difference operator. So what's a forward difference operator? Have you have you ever seen something somewhere called the forward difference operator? So we can say that the forward difference operator denoted by this symbol is defined as, so the forward difference operator of a function f of x is given by a function of f of x plus h minus f of x. So it's just basically the difference in the value of the function when you move one step ahead. And remember, so if we let x to be the same as xk, then that means what? That I have here, this is a function of xk is the same as f of xk plus h, then minus f of xk. But remember the notation I defined here. I can use this in terms of y. That means that's yk is the same as. So if f of xk is equal to yk, what will be f of k plus h? Can somebody tell me what will be the value of y? How do we define it in terms of y?
Come up again, please.
If f of xk is denoted as yk, how do we denote f of xk plus h?
Y of k plus h.
Y of
K plus h.
k plus h. Somebody else? So x1 is x naught plus h. x2 is x1 plus h, right? So if you notice this, what is xk plus h? What's xk plus h?
xk minus 1 plus 2h.
Xk minus 1 plus 2h. No, but we are now going back. Can we go forward? What is xk plus h? Recall we said h is the height. And so if you are at the point k, that means you have xk, and then you move one step ahead. Which value do you get?
xk plus 1.
Yeah, so this is xk plus 1, and then minus yk. Basically, so when I want to do this in terms of the notation, then this is what the forward difference does. If you are at this point k, meaning you have xk, you move one step ahead to the next value k plus 1. That means you have xk plus 1, and then you find the difference of the values of the function at this point. So you are moving one step ahead, and then you find the difference of the value ahead. So that's why it is called the forward difference operator. You are looking ahead. And so that's called the fast forward but I didn't say something here. Maybe I could have said here that this is called the fast forward difference operator, because you are doing this operator once. So that's the fast difference forward difference operator. And then in the same manner, we can define the second difference operator. So we can say just here that in the same way, the second difference operator denoted, that is this squared, is given by or is defined as, so is the second difference operator of f of x. And just so the second difference operator is the first forward difference of the first forward difference. I don't know if I'm making sense. It's a forward difference of the first forward difference. Basically, I mean that I can write this as what? Forward difference of the first forward difference operator. That's now the second difference operator. But we recall this formula. I can just quickly define this in terms of this. So I have the first difference operator of yk plus 1 minus yk. So it means I'm having a forward operator of the two functions. This can, did you do somewhere groups? Rings, groups, what? Binary operations? Sometimes I don't believe no ya wanafunzi. It can be true, but no, but it just there's something. If you look at the properties of integers, that multiplication is distributive over addition. Basically, I can distribute this over this. It's just what you call in other terms that you are opening the bracket. So I correct this as forward difference of k plus 1, then minus forward difference of k. So can somebody tell me what's the forward difference of yk plus 1? Using the same definition we called about the forward difference.
It should be forward difference of yk plus 2 minus forward difference of yk plus 1.
Are you saying the whole of it or only this one?
Only that one.
But now the forward difference is gone. So you will have, this is yk plus 2. You move one step ahead and then subtract the value of your current position. And then this will give you yk plus 1 and then minus yk. And so if you combine this, that means yk plus 1 is the same as what? Yk plus 2 minus 2yk plus 1 and then plus, I have negative, negative. So yk. So once you perform that difference operator, then the other difference operator goes. So you can define the third difference operator in the same way. It's just, so like for example, if I have here the third forward difference operator of yk is the same as what? Is first difference operator of, or if I put here 1, then I have yk. But it's also the same as second difference operator of the first difference operator. You cannot, I think they call this is associative property. You can open the bracket as you go, start with the inner one, followed by the other one, and then you keep on moving. So following this manner, we can say that in general, the end forward difference operator denoted n is defined as, so when you have the n forward difference operator of yk is the same as what? Is n minus 1 yk plus 1 minus n minus 1 yk. That is so where n is equal to 1, 2, 3, and so on, and with yk is the same as yk. So we are constructing here a recursive relation. Do you know what I mean by recursive relation? If I say recursive relation, do you know what I mean by recursive relation?
Is it something repetitive or?
Yeah, something repeated. So you're just changing indices and then you keep on. So the current value or the current operator uses the previous operator. Then the previous operator uses the previous, and so on until you get the starting point. So if you define the initial value, you are having a function that calls itself. So if I say, for example, I want to evaluate the 10th difference operator, it will first call itself, rotate, go back to 0, and then start now generate coming back. Right? So that's what I mean by recursive relation. And you can even program, once you know that this thing is what is happening, given initial condition, you can generate all the other values. Somebody says you find the 10th difference operator, then you just call this function on itself. Any question until that point? We want to define some things, but maybe let us just first of all do just an example, one with data values and the two with functions. So given the function f of x, for example, is the same as x cubed plus 2x squared plus ax plus b. 1, find, that is delta f of x, delta squared f of x, delta cubed f of x, and hence reduce delta n f of x for n greater than or equals to 4. So 2, given the scenario above, what can you say of, so you have the nth difference operator of f of x, where f of x is a polynomial of degree n. Maybe just written in this form, you have x plus n, then plus, you pick these values as you go on. So maybe you know, let us just first of all look at this. I just made this cubed, but since we want to understand, let me just start by making this simpler one. Let us just do the same thing, but on this simpler. So I can write this as x squared plus ax plus even, let me just put here too, any number, then plus, give me any value to put here, or any letter. B. So I'm just avoiding this as an example because it will involve a lot of expansion. So this is much quicker to deal with. So the solution, we have that our f of x is the same as x squared plus 2x plus b. And so recall that data of x is given by f of x plus h minus f of x. Do you recall finding limit from first principle? Do you know definition of a limit by first principle?
Yes.
Can you use some relationship with this? Do you?
Yes, yes.
Yeah. So these things are basically related to derivatives. It's just only that now we are finding the derivative and then we are just approximating, not derivative at a point, taking a derivative in the interval. And so when you have this, just plug in here. It means in the first case, maybe let me try to be slowly. It means where there is x, I'm replacing with x plus h. So I'll have x plus h squared, and then plus 2 into x plus h, and then plus b. And then f of x it just remains the same. That is x squared plus 2x plus b. So if you subtract, what do you get? B will go, 2x will go. I remain here with the 2h. So here x squared will go. I remain with 2xh plus h squared, and then plus 2h. Is that okay?
Yes.
Yeah. So I'm just expanding. So if you know, you can just expand this slowly. Now, so it means the second forward difference of this the same as the first forward difference of the first forward difference. But already we have this, which is given here. So I'm just performing the first difference operator on this, which will give me 2x plus h multiplied by h, and then plus h squared plus 2h. Is that okay? Then subtract 2xh plus h squared plus 2h. I'm subtracting this. These two guys will go. 2xh will go. And then I remain with what? I remain with 2h squared, right? Yeah, can you confirm that that is 2h squared? And this being a constant, it means all the subsequent ones. So it means f of x will be the same as 0 for n is equal to 3 and above. Because now we have gotten a constant. And that's the result I wanted you to comment on in this part. That if you have a polynomial of degree n, then the nth forward difference is the same as what? N factorial h to the power n. So this says energy saver turned on. Okay. Let me sort out this. It says energy saver turned on. Might start sleeping before we wake up. But until this point, is there any question? Remember that I'm being a bit slow on the forward difference operator, but when it comes to the backward, I may go a little faster because they will just be the same thing. It's just only that instead of looking ahead, we are looking back. So you can finish up this. So it means here, if you find the third difference here, if you look at this function, the third difference. So here, the third difference of will be the 3 factorial h to the power 3. And so it means, and anything above 3 gives you 0. And so the conclusion here is the same thing. If you have a polynomial, the nth difference operator is given by this, is n factorial h to the power n. Then you multiply. So that's basically what I wanted you to conclude at that point. Can you do the same things when you have such functions? For example, e to the power x, or you have f of x is equal to sine of x. It's just basically you try to see if you can get a simpler function. You get something related to a derivative. Now, but so our interest, remember, in this course was to get the difference operator functions evaluated at tabular points. And so what we do, I think maybe this I will look at it in form of a table. I think I can first give some results here. Just let me state something like a theorem, which might be important, but maybe don't need to prove it. So we can show that, so the nth difference operator of yk can be in terms of what? The combination of these values. So j is equal to 0 until n. Then you have -1, that is n minus j, and then any combination j into yk plus j. So that's so if you use this formula on a 2 by 2, so you are summing up this, it should give you what we got here. So basically, I'm just generalizing this. It's just operating on different operators. But this one, you don't need to, I'm just giving you, but you don't need to cram this formula. Maybe you may not even write this anyway. But basically, this is the general form. So the simplest way of looking at these four differences is constructing what we refer to as the difference for a difference table. So you can just write here the notas in B. The simplest way of evaluating the four differences is by difference table. And so the table looks like this. So you have a column for xi. Some people have a column for I if you want. Can I delete? And then I can press delete. Okay, so it works. So some people have here a column for I, and then a column for xi, and then a column for yi. These are what you are given. So I is 0, I is 1, I is 2, I is 3, I is 4, I is 5. So depending on the data points you have, you'll have x0, x1, x2, x3, x4, and x5, and the corresponding y values. Then you start now forming different columns for the differences. So I have the first one here is first four differences. And then you fill this table, and there are several. If you read different books, you will get different formats of these four difference table. I am going with the diagonal difference table. That means the difference between two quantities is written at the middle. And so, for example, here, the difference between this and this, I note it as, remember, when talk of four differences of y0, it's now y1 minus y0. So this is given by y1 minus y0. I'm just writing this so that you know, so that the others are not write this. And then, so the difference between this and this is what? This is delta of, can you tell me what I should fill here? What I should fill here? 1 minus y0.
delta y1,
y1,
y2,
y2,
y3, and y4,
y3,
y4.
and y4. Now we have a column for second forward differences, right? So here, you know that all of them will be y squared. This is y squared. This is y squared. This is y squared. This table will proceed, but maybe just to explain something. Can you check if I find this squared here? It is so it's so it means it's a forward difference of y1 minus y0, right? That means it's a second forward difference of what? In short, I'm asking which value should I fill here?
Why not?
Y0. And this will be y1, this will be y2, this will be y3. So if you take the forward difference of these two, it means is so basically this table follows this line. That's why you call it the diagonal table. And then if I go here to yi, so using in the same manner, so this will be y0, this will be y3, y1, and this will be y3, y2. So if somebody asks you, for example, to find the third forward difference of y0, and you have this table, then you just know the value you come to pick. And so this is y4, yi. This will be y0 4, and this is y4, y0. And if this is y5, yi, then this will be what? 5, y0. So it's different table. So that's why I'm calling it different table. So if you follow the diagonal downwards, so basically you are getting those values just by following what? By following the diagonals. Let me use maybe a smaller one to try to follow. For example, if I want to follow y0, then I just go here. Then I can follow the values of y0. If I want y1, then I can get y1. If I want 2, if I want y3, if I want y4. It means for y5, I cannot get any forward difference for y5. But we will see later. The reason why I like this diagonal table is that the forward difference table and the backward difference table are basically the same thing. They'll have the same values here. What differs will be the interpretation. That if I look at the backward difference table, the value here will be now the backward difference of y1, but it's basically the same as this value. Is that okay? So come up with a difference table for the following. So I have xi. Is this green clear? Let me use a different one. So that is 0. Let me go back to this. My friend is the good one, maybe. That's 0.05. I have 0.1, then 0.11, 0.2, 0.26. That is 0.3, 0.35, 0.4, 0.49, 0.5, then that is 0.67. So we can construct the difference table here by first of all having xi. So that is 0, 0.1, 0.2, 0.3, 0.4 until 0.5, right? So remember, as we have seen in this table, that if you have a mistake, for example, in this value here, then this mistake will propagate downward. So it means all these values here will be wrong, including this value. So it will propagate downwards. No, not here. So it will follow this line. So it means anything here will be affected by y1. So you can go and check how can you follow back to remove errors in a forward difference table, assuming I identify that I have a table and somebody tells that this value is wrong. Can you get the correct value so that this table is correct? If said you know Nando, right?
Yeah.
You can ask him that I asked him to, he can give you this, he has. And I think it's in his YouTube channel. So you can go and follow his YouTube channel. You see what happens if you have an error in a forward difference table. 0.11, 0.26, 0.35, 0.49, 0.67. So can you give me yi here? And so on, depending on where you finish. Can you give me these values? But these things are the things you use calculator. I think this is 0.06. And then here, this is what? This is 5. This is 1. 0.15. And then this is 9. I think this is 0.9. Can you confirm? This is 4. 0.14. This is 7. That is 8. 0.18. Can you confirm if these values are correct? And then here, if you subtract 15, that is 9. That's 0.09. This is 0.09 minus 15. Ooh. That is 0.06, but negative. This 0.14, that is 14, that is 5. That's 0.05. That is 0.04. But I'm getting these things, and you have calculators.
They are correct.
Now you should get at least you should finish up. So now give me these other ones. That's negative 0.15. I think it will be the same as this. And then when I'm subtracting here, so I'm adding, that's 0.11, right? and then this negative 0.01 negative. And then so if subtract here, you are adding 0.26. If I'm subtracting this, I am also adding the negative 0.12. If I subtract this, I'm adding, but now negative. That's 0.38. Can you confirm if those values are correct?
Yes, they're correct.
Na kwani mlikuwa mmenyamaza? Ama mlikuwa ama mjakunywa chai? Mnataka mengere? So now from that table, can somebody, for example, give me this difference of y3, fourth difference of y5, that's y naught, that's x naught, 0, 1, 2, 3, 4, 5. So can somebody give me these values? Just the randomly, I'm just picking values. So can you tell me the answers? Because you pick in the table, yes, you have to know.
Negative
that.
0.01.
That is for which one?
The first one.
Negative 0.01. We will confirm. What is delta for y5? Anybody?
Null.
Okay, yeah, does not exist. And delta 5 of y2?
It's also null.
Also none. That's correct. Does not exist. Because remember, I said the horizontal table. So you are following this. So this is anything to do with y naught. Right? And then the next one here is something to do with y1. So if you are asked about y1, then you follow this. Then if somebody is asking about y2, then you follow this. So for example, if I want the delta cubed of y2, then it's here. But delta 4 of y2, I don't have it. It does not exist. So this is just horizontal. So once you draw the arrows, then you can find all the possible values you want. Until this point, is there any question? So if not, maybe we can now define the backward difference. Backward differences. So since we have seen the other difference tables, now is I just here go quickly. So the first backward difference denoted. So this one we have the, is it called the nabla, or the other is the nabla? One of them is this, one of them is nabla. But this is facing downwards. Is given by, so the backward difference of f of x is same as what? Is f of x minus f of x minus h. So you are basically, what I said, you look back from where you are standing at, and then you move one step back, and then you get the differences. That's the backward difference. Using the y notation, then it's written as what? Backward difference of yk is yk minus 1. And so using the same notation, can somebody find the second backward difference? It's basically, so having second backward difference of f of x is just the same as backward difference of the first backward difference of that function, which give us what? Backward difference of yk minus 1. And if you do this, that will be
Excuse
yk. Eh?
I think in the previous step you wrote the operator for forward difference.
Oh, sorry. Okay. So this has to be backward. And then plus yk minus 2. So this can be written as what? Yk minus 2, yk minus 1, and then plus yk minus 2. And if you check well, this is the second forward difference operator of yk minus 2. And so what does it tell you here? That the backward difference operator of yk is the same as the forward difference operator of yk minus 2. That means the backward difference operator, third one of yk, be the same as the third forward of yk minus 3. So you can start getting those connections. And most of the things we have done above, even those examples, even the polynomial, it also holds for the backward differences. So you can now say here that in general, the nth backward difference, just basically yn is the same as what? Is the backward, that's less 1 yk minus yk minus 1, given if you take just this is index 0 is the same as the same value. We are just sticking at that value. And so note the other thing I mentioned to you, that the nth for the difference operator of yk is the same as the nth backward difference of yk plus n. Or you can write the other way, the same. I write the other one. Backward of yk is the same as forward of backward of yk is the same as forward of yk minus n. They are the same. And so the table I've mentioned to you, this table I wrote here, is similar table with the backward differences. The only it will contain the same values exactly, but now with different interpretation. So I can just write here maybe a few examples just to show. So I have here the x, I have the y. So this is x0, x1, x2, x3. Let me just only write these three values: y0, y1, y2, y3. And then I have backward difference of y. So this is what? Backward difference of y1, backward difference of y2, backward difference of y3. And if I have y, this is backward difference of y1, this is backward difference of y2. And if I have this is backward difference of, did I make a, no, this is a backward difference of y2, and this is a backward difference of y3, and this is a backward difference of what? Of y3. So you see that for the backward differences, we are now looking up. So for example, if you look at this value, if you look at this table, we can still read the backward differences in this. But for the backward difference, we are looking at the back. So if you look at this value, is the fifth forward difference of y naught, but the same value is the fifth backward difference of y5. So the forward difference table and the backward difference table are the same. Maybe I can put this comment here. Forward difference table and backward difference table are the same, but with different interpretation. So it's just basically the same table. So if you are making the forward difference or making the backward difference, you are having exactly the same table. You will just interpret the values, inputs differently. Mwaurire. So what is left? I don't know how much time is left. Maybe we'll look at this next time, and we'll look at the relationships between these operators, and then we'll look at now the polynomials. But if you find your own time, you can go and look at this central, what we call the central difference operator. No, maybe I can, let me just write them down. So the central difference operator is just what? You are moving one step ahead, a half step ahead, and then subtract a half step back. So if I have here, this is k, then I move one step here to k plus a half, and then I move one step to k minus half, and I get the differences. So basically, it's written the delta. So this forward difference of yk will be the same as yk plus a half minus yk minus a half. And then we will see what this means. For example, what is squared of yk? This will mean is the forward difference of the forward difference of what? No, not forward, central difference of yk. That means is central difference of yk plus a half minus central difference of yk minus a half. And can somebody tell me, using this definition, what is this forward? No, what is the central difference of yk plus a half? What is the forward difference of central difference of yk plus a half? You just move a half step ahead. So it is yk plus 1 minus yk, because I'm just subtracting a half. And then subtract, this is yk, and then plus, I'm adding then yk minus 1. This gives us yk plus 1 minus 2yk, and then plus yk minus 1. But what is this value in terms of the forward differences and the backward difference? What is that value? If you recall, this is second forward difference of yk minus 1. And it's still the same value as second backward difference of yk plus 1. So the central differences in the table, they coincide with the difference table at the even points. So if you check this table at only the even differences, then they will coincide. Otherwise, they don't coincide. So if you go to for example the y naught, it comes only, you are here, I think it does something like this, and then you only start coinciding at the intermediate values. So we will look at the relationships between these differences or periodic difference tempos maybe in the next class. Let me just today make sure that I give you the definitions. Next, we look at the shift operator. So the shift operator is just saying that move one step ahead. So this is just f of x plus h. I'm just shifting you one step ahead. That means the shift operator for yk is the same as what? Yk plus 1. You look one step ahead. Shift squared operator of yk, just look 2 steps ahead. So yk plus 2. Shift minus 1, yk is the same as yk minus 1. Look back 1 step. So you just look at the power. In general, n yk is the same as yk plus check look n steps. So that's just the shift operator. And some of these operators are important, though here maybe we'll only look at the forward and backward mostly. And maybe to some extent we may look at the central or the averaging. So lastly, we look at the averaging operator. So the averaging operator denoted mu of f of x is just what? The average between the shifted values at a half. So that is f of x plus a half, then plus f of x minus a half. Or in terms of yk, I can say that mu of yk is the same as, let me use 0.5 here. Then that is what? Yk plus a half, and then plus yk minus a half. It's almost related to the central difference of the central differences. But you are subtracting. Here you are finding the average of those values. So it means you can also define these values, like if you want a mu squared of yk, then you are finding the mu of you are finding the average of the average. So in the next class, I'll just briefly look at some. No, I want you to go and write this down. Relationships between the difference operators. So go and look at them. Then the next class we'll discuss them as we go on. It's not an assignment, but I want you to look at them, because in an exam, I may ask you to prove this. Just for example, can you show that the shift operator is the same as 1 plus the forward operator? Can you show that this product is equal to 1? Can you show that the shift operator is 1 minus backward to power minus 1, and then and so on? So I think the relationships are so many. So just can you make sure that you try to read them and understand these operators? Let me see if I have others somewhere. Let me try to look. I'm trying to check this if we have some relationships. I think this is just basically this one. I think this one also can be written as what? The forward difference operator is the same as 1 minus this, and then minus 1. And then the averaging operator is shift a half minus shift minus half. But that is easier. This is easier to prove, because if you look at this averaging operator is given by this. So this is the same, but this is the same as what? This is E a half yk minus E negative a half yk. Now I can take yk outside and then do that. So this is how you define all of them. Some of them you prove this way. Just start from the relationship, simplify, put out yk, and then you equate. So just make sure that you try to go through some of these relationships, understand how they are derived. Some of them you can derive from others, while others you need to derive them from the basic principles. Just start from the definition of what this means. I think those are enough. Others are, but these are enough to just to show you you look at the relationships, so that next time when I'll just review this, a few of them, and then we start on Newton's interpolation formula. And I should finish this Newton interpolation formula in the next class. So I look at both the forward and the backward. And after one class, I look at the Lagrange's interpolation. And so having looked at the Lagrange, then I will. When will you do the exams?
On the 3rd of June.
Oh,
We
so
are
how many
starting
weeks?
exams. Oh,
It should be
wait,
4th.
2 more weeks.
But we need to cover some of these things so quickly.
2.
So do you have some other time you may do the presentations, except Tuesday and Thursday? If we have Tuesday and Thursday, because one of the key topics I want us to look at least to look at
Okay.
is yeah. Sorry. Somebody was saying something. that now since you have the textbook and we get so you can read a bit some of the things slowly, but I'll try to make sure that I cover almost at least I give you highlight of what you need to cover, and that's what the exam will cover. But so we need to finish this topic at least interpolation, and then we do the Lagrange's interpolation, and I look briefly at the we need numerical integration, and also now integration of ODEs. Can you present on weekends the assignments? Now that EPL is going.
That's not very much promising. We got our SDA brothers, many of them from our class, so I don't know.
You got? No, can you discuss?
SDA
Go and
brothers.
find it. Another time you can present some other time. And then let me know. Outside Tuesday and Thursday. If we have, I think, 4 or 5 classes there. So next week, two. If we have 4 classes are enough to finish. So if we can put presentations outside, it will be okay. Otherwise, what we can do is we can forego the presentations, but now I let you to work on those assignments I give you, all of them, and you will submit the write-ups. So let us see. We may forego the presentations, but you work on the assignments I give you, and then you submit them. That okay? But just be ready in case we may present, but if not, we will just submit them and then I'll mark them without you having to present. Okay, yeah, that's enough. We can call it a day.